February 19th, 1944, Kwajalein Atoll, Marshall Islands. Commander Tatsuo Shimada of the Imperial Japanese Navy's Technical Research Department stood amid the wreckage of what had been garrison headquarters just 6 days earlier. American shells had torn through the concrete structure, scattering documents and equipment across the coral sand. But Shimada's attention fixed on a single manila folder, water-stained and torn, retrieved from a filing cabinet that had somehow survived the bombardment. Inside were typewritten pages that would explain a mystery costing the Imperial Navy ships, at an accelerating rate, a hemorrhaging of cruisers, destroyers, and transports that threatened Japan's ability to defend its oceanic empire within months. The technical specifications detailed in those captured American documents described radar systems that rendered every assumption of Japanese naval doctrine obsolete. What neither Shimada nor his superiors in Tokyo yet understood was that these papers would reveal not just superior technology, but evidence of an electromagnetic dimension of warfare in which Japan had been fighting blind while American forces possessed omniscient vision. The psychological transformation that would reshape Imperial naval strategy had begun on that debris-covered island, though the full implications would take weeks to comprehend. The invasion of Kwajalein, designated Operation Flintlock, had commenced on January 31st, 1944. American forces under Admiral Raymond Spruance's Fifth Fleet had landed on the atoll after a devastating preliminary bombardment. The Japanese garrison of 8,000 men under Rear Admiral Monzo Akiyama had fought with characteristic determination, but American material superiority had proven overwhelming. By February 7th, organized resistance had ceased. Among the American units that participated in the assault were multiple Fletcher-class destroyers, including USS Fletcher, herself, the lead ship of the class that had revolutionized American destroyer design. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. These destroyers, commissioned beginning in 1942, represented the first American warships designed from inception to carry radar as integral combat equipment. At 2,050 tons, standard displacement and 376 feet in length, they were substantially larger than previous American destroyer classes, growth necessitated partly by the volume and weight of electronic equipment that would define naval warfare's future. Each Fletcher carried multiple radar systems, an SC air search radar capable of detecting aircraft at ranges exceeding 70 miles, an SG surface search radar that could identify ships at the horizon's edge even in complete darkness, and Mark 12 fire control radar that guided 5-inch gun batteries with unprecedented accuracy. Commander Shimada had arrived at Kwajalein as part of a hastily assembled technical intelligence team dispatched from the Combined Fleet Intelligence Section in Tokyo. His specialty was communications, electronics, and he had been among the few Japanese officers who understood that American technological advantages in radio and radar posed existential threats to Japanese naval operations. The assignment to Kwajalein came with explicit orders from Admiral Minechi Koga, Commander-in-Chief of the Combined Fleet. Determine what electronic capabilities the Americans possessed, assess whether Japanese countermeasures existed, and report immediately any intelligence that might affect operational planning for the defense of the Marianas. The folder Shimada recovered contained maintenance logs and operational procedures for American SG surface search radar. The documents were routine, the sort of technical manual that would accompany any piece of equipment through its service life. But to Shimada's trained eye, they were revelatory. The SG radar, according to these captured specifications, operated at 10 centimeter wavelength in the microwave spectrum. Peak power output reached 50 kilowatts. Detection range for large surface vessels exceeded 25 miles in optimal conditions. The antenna rotated continuously, providing 360-degree coverage, with returns displayed on a circular plan position indicator scope that showed bearing and range simultaneously. The system weighed less than a ton, could be installed on vessels as small as patrol craft, and required fewer than a dozen vacuum tubes in its critical circuits. Shimada sat on a chunk of broken concrete, spreading the documents across his field desk. He checked the specifications against his knowledge of Japanese naval radar. The comparison was devastating. The Imperial Navy's Type 22 radar, their most advanced surface search system, operated at 10 centimeters but generated only 2 kilowatts of peak power, 25 times less than the American SG. Japanese radar sets, even when they worked properly, detected large ships at perhaps 20 miles maximum range, and then only when sea conditions remained calm. The Type 22 suffered chronic reliability problems. Vacuum tube quality was abysmal. Often fewer than 1 tube in 100 actually performed to specification, and even those that did had mean time to failure measured in mere hundreds of hours. Ships' captains routinely ordered radars shut down during operations, fearing the transmissions would provide homing beacons for American direction-finding equipment while delivering negligible tactical advantage. But the SG radar represented only part of the American electronic arsenal. Additional documents described the SC air search radar, operating at 1.5 meters wavelength, detecting bomber formations at 75 miles distance. Height finding, radars. Fire control radars that could track individual shells in flight and adjust aim to hit targets at maximum gun range. Most disturbing of all were references to combat information centers, specialized compartments, where radar data from multiple sensors fed into plotting boards, enabling commanders to maintain awareness of tactical situations across vast ocean areas simultaneously. The Americans had not merely developed superior individual components, they had integrated electronics into every aspect of naval operations, creating a system that provided commanders with comprehensive understanding of battlespace far beyond the horizon. Shimada's immediate superior, Captain Ryunosuke Kusaka, joined him among the ruins. Kusaka commanded the Technical Research Department's analysis section and had spent the previous day interviewing captured Korean laborers who had worked on American installations. "What have you found?" Kusaka asked, settling onto a twisted beam that had once supported the headquarters roof. "Evidence of capabilities we cannot match," Shimada responded, handing over the maintenance manual. "The Americans can see in darkness as clearly as we see in daylight. Perhaps more clearly, because their radar penetrates weather that would blind optical observation." Kusaka examined the documents, his expression darkening as he read. 25 miles detection range? Documented performance, Shimada confirmed. And I suspect actual operational capabilities exceed these specifications. Maintenance manuals describe minimum performance standards, not maximum capabilities under ideal conditions. If American destroyers can detect our ships at such distances, Kusaka said slowly, reasoning through implications, they hold advantages in every engagement. They see us before we see them. They track our movements while remaining beyond our detection range. They choose whether to attack or evade, while we react blindly. It explains the encounter reports, Shimada agreed. The two officers had reviewed dozens of action reports from Japanese cruiser and destroyer commanders over the previous year. A consistent pattern emerged. American vessels appeared to possess supernatural awareness of Japanese positions and movements. Japanese night attacks, traditionally Japan's tactical advantage, repeatedly failed as American ships opened fire from beyond visual range, guided by sensors Japanese observers could not detect. Surface actions that Japanese doctrine predicted would favor superior Japanese torpedoes, and night fighting training instead became slaughters, as American radar-directed gunfire bracketed Japanese ships before they could close effective weapons range. The psychological impact on Japanese naval officers had been profound, though officially unacknowledged. A service that prided itself on superior training and warrior spirit found itself consistently outmaneuvered and outfought by an enemy that seemed omniscient. Explanations varied: American code-breaking, submarine reconnaissance, aerial observation, but none fully accounted for the consistency and precision of American tactical knowledge. Now, examining captured documentation, the truth became inescapable. American technological superiority in radar provided omniscience that Japanese training and courage could not overcome. The historical antecedents of this technological gap extended back years before the Pacific War began. The United States had initiated serious radar development in the late 1930s, building on British research shared during the Tizard mission in 1940. That mission, named for British physicist Sir Henry Tizard, had brought to America the cavity magnetron, a revolutionary device that generated microwave radio frequencies with power and efficiency impossible through previous designs. The magnetron, invented at Birmingham University in 1939 to 1940, made possible compact, powerful radar, systems operating at centimeter wavelengths. These microwave radars could detect smaller targets at greater ranges with higher precision than earlier meter wavelength systems. American industry, already the world's largest and most sophisticated, had transformed British laboratory prototypes into mass-produced operational equipment with remarkable speed. The Massachusetts Institute of Technology's Radiation Laboratory, established in October 1940, coordinated radar research and development across dozens of universities and hundreds of corporate partners. By 1942, American factories produced radar sets by the thousands. Fletcher-class destroyers, designed specifically to carry this equipment, entered service with complete electronic suites as standard installation. The SG radar alone had over 14,000 units manufactured during the war, more than all Japanese radar production of all types combined. Japan's radar development followed a different trajectory. Japanese scientists had independently developed some radar principles, including early magnetron designs. In 1937, the Imperial Japanese Navy's Technical Research Department had constructed cavity magnetrons operating at 10 centimeters. This represented genuine scientific achievement, accomplished without knowledge of parallel British work. But Japanese military leadership failed to recognize radar's operational potential until far too late. While American and British forces deployed comprehensive radar networks by 1941, Japanese development remained in experimental stages. Even after Pearl Harbor demonstrated American radar's tactical value, American SC radar detected the incoming Japanese strike force. Though commanders failed to react appropriately, Japanese development programs received inadequate resources and priority. Inter-service rivalry compounded technical challenges. The Imperial Japanese Army and Navy refused to cooperate on radar, research, duplicating efforts, and diluting scarce resources. Each service developed incompatible systems, unable to share components or operational data. Critical materials, especially nickel required for vacuum tube production, became increasingly scarce as Allied submarines severed shipping routes. Quality control collapsed as production was subcontracted to small firms lacking expertise. American intelligence assessments after the war concluded that Japanese radar sets, even when functioning, typically failed after mere hundreds of operational hours. Many never functioned at all. The electromagnetic advantage passed decisively to America by mid-1943, and the gap widened thereafter. Commander Shimada gathered his documents as tropical dusk descended over Kwajalein. The captured papers would be shipped to Tokyo aboard one of the few submarines Japan could spare for transport duties. Analysis by the Technical Research Department's senior scientists would confirm what Shimada already understood. American radar technology exceeded Japanese capabilities by margins measured not in percentage improvements but in orders of magnitude. This knowledge would reshape or should reshape Japanese naval strategy for the war's remainder. But strategy predicated on inferior technology faced grim mathematics. Japan could not match American electronic capabilities with existing resources. Industrial capacity to produce radar components at American scales did not exist. The specialized technical workforce required to design, manufacture, maintain, and operate sophisticated radar systems had never been developed. Yet tactical adjustments might mitigate some disadvantages. If Japanese commanders understood they faced enemies with comprehensive radar coverage, they could avoid engagements where American sensor advantages proved decisive. Night surface actions, traditionally Japanese strengths, should be abandoned except when surprise precluded American radar deployment. Operating under radar silence might deny Americans some intelligence, though this also eliminated Japan's own radar utility. Aircraft operations could be planned to approach targets from directions that maximized terrain masking, reducing American radar's effective range. Submarines, which operated underwater beyond radar detection, might assume greater importance in fleet actions. These were defensive measures, acceptance of technological inferiority, adaptation to American superiority. They were not strategies for victory. Shimada understood, standing among Kwajalein's ruins, that the captured documents described instruments of Japan's inevitable defeat. An enemy that could see while Japan remained blind held advantages no amount of courage or tactical skill could overcome. The mathematics were unforgiving, the physics were inescapable. The strategic implications were catastrophic. Captain Kusaka joined Shimada for the short walk back to their temporary headquarters in a captured American bunker. "Your report will not be popular in Tokyo," Kusaka observed. "The Naval General Staff prefers to believe we maintain qualitative superiority over American forces. Your analysis demonstrates the opposite, that American technology provides overwhelming tactical advantages we cannot counter." "Popularity is irrelevant," Shimada replied. "Accuracy is essential. The combined fleet requires honest assessment of American capabilities. False optimism serves no purpose except to send our ships and men into battles they cannot win." "Truth is not always welcome," Kusaka said, "especially when truth is humiliating." They walked in silence past American landing craft beached on the lagoon shore. These vessels, ungainly but functional, represented another dimension of American material superiority. Purpose-built amphibious ships, produced in numbers that overwhelmed Japanese defenses. Each assault brought more ships, more aircraft, more radar sets, more of everything industrial capacity could manufacture. Japan, its factories bombed and its shipping strangled by submarine blockade, could not replace losses at rates approaching American production. The war had become attritional, and attrition favored the side with deeper reserves. The psychological weight of this realization pressed heavily on both officers. They were professionals, educated in naval engineering and tactics, trained to assess capabilities objectively. The evidence before them admitted no optimistic interpretation. America's industrial and technological superiority would grind Japan down regardless of individual battles' outcomes. Radar represented one component of that superiority, but American advantages extended across every dimension of military capability. Superior aircraft, superior ships, superior weapons, superior logistics, superior training systems that produced competent crews faster than Japan could destroy them. And superior technology radar being merely the most visible manifestation that multiplied all other advantages. That night, Shimada drafted his preliminary report by lamplight in the bunker. He wrote in clear, precise language, avoiding both technical jargon and emotional rhetoric. The facts required no embellishment. American SG surface search radar provided detection capabilities exceeding Japanese systems by factors of 2 to 5, depending on conditions. American SC air search radar detected incoming aircraft at ranges that gave defenders minutes to organize responses, where Japanese radar provided seconds or no warning at all. American fire control radar directed guns with precision that Japanese optical rangefinders could not match, even in perfect visibility. American combat information centers integrated sensor data in ways that gave commanders comprehensive battlespace awareness, impossible through traditional methods. And American industrial production equipped ships with these systems as standard installation, while Japanese vessels operated largely blind. The implications section of Shimada's report laid out consequences with stark clarity. Japanese surface forces operating within American radar range faced detection before they could detect enemies. Japanese aircraft approaching American defended positions would be tracked from distances that permitted organized defensive responses. Japanese submarines, when surfaced, could be detected before they achieved favorable attack positions. Japanese defensive perimeters around key bases would be mapped by American radar, eliminating any hope of tactical surprise. Japanese offensive operations could not rely on nighttime concealment or weather conditions that previously provided cover. In every scenario, American radar superiority provided tactical advantages that Japanese commanders could not overcome through superior training, better tactics, or exceptional courage. The only recommendations Shimada could offer involved damage limitation rather than victory. Japanese forces should avoid surface actions against radar-equipped American ships unless surprise could be achieved or overwhelming numerical superiority applied. Japanese aircraft should approach targets at extremely low altitudes, exploiting radar's limited ability to detect objects masked by terrain or sea clutter. Japanese operations should prioritize nighttime and poor weather, accepting reduced effectiveness for some concealment from omnipresent American sensors. Japanese submarines should surface only when absolutely necessary, minimizing exposure to American radar. And Japanese leadership should accelerate programs developing countermeasures against American radar, though Shimada held little hope such programs could achieve meaningful results given Japan's industrial limitations. He signed the report, sealed it in a waterproof pouch, and handed it to the courier who would carry it to Tokyo. The document would reach the Naval General Staff within a week. Whether its recommendations would be implemented or even acknowledged remained uncertain. Japanese military culture privileged offensive spirit over defensive realism. Acknowledging technological inferiority contradicted institutional narratives of Japanese superiority, yet failure to adapt to American radar advantages would cost ships and lives to no purpose except maintaining face. Shimada could only hope that pragmatism might overcome pride before attrition eliminated the combined fleet entirely. Over the following weeks, additional intelligence reached Japanese analysts that confirmed and expanded on the Kwajalein discoveries. Documents captured at other Marshall Islands installations described American radar deployment across the Pacific Theater. Battle damage assessments from returning Japanese pilots reported American fighter aircraft intercepting Japanese formations with precision that suggested comprehensive radar coverage extending hundreds of miles from defended bases. Japanese submarine commanders reported American destroyer groups detecting and attacking Japanese boats at night, despite cloudy conditions that should have provided concealment. A pattern emerged, consistent and undeniable. American forces possessed sensor capabilities that rendered traditional Japanese tactical approaches obsolete. The Imperial Japanese Navy's response to this intelligence proved hesitant and incomplete. Some commanders acknowledged American radar superiority and adjusted tactics accordingly. Admiral Jisaburo Ozawa, commanding the mobile fleet, emphasized operations during weather conditions that degraded radar effectiveness, and trained his pilots in low-altitude approach techniques designed to evade radar detection. Other commanders dismissed radar as mechanical contrivances inferior to Japanese fighting spirit and continued operating under doctrines predicated on technological parity or Japanese superiority. The Naval General Staff issued directives acknowledging American radar advantages but failed to provide resources necessary for comprehensive countermeasures development. Japanese industry, already struggling to maintain warship and aircraft production, could not divert capacity to electronics manufacturing at scales that might have narrowed the radar gap. By mid-1944, the tactical implications of American radar superiority had become undeniable through bitter operational experience. The Battle of the Philippine Sea in June 1944 demonstrated American radar's decisive impact on carrier operations. American fighters, directed by radar controllers, intercepted Japanese strikes so effectively that American pilots nicknamed the engagement the Great Marianas Turkey Shoot. Of 400 Japanese aircraft committed to the battle, fewer than 100 returned. Japanese losses included 3 fleet carriers sunk, crippling the combined fleet's ability to conduct further large-scale carrier operations. American radar had transformed carrier warfare from contests of skill and luck into systematic slaughter of forces operating without equivalent sensor coverage. The surface navy fared no better. At the Battle of Leyte Gulf in October 1944, American radar again proved decisive. During the Battle off Samar on October 25, American escort carriers and destroyers of Taffy 3 faced Vice Admiral Takeo Kurita's center force, 4 battleships, 6 heavy cruisers, 2 light cruisers, and 11 destroyers. Despite overwhelming Japanese superiority in gunfire, Kurita's force failed to destroy the vulnerable American carriers. Multiple factors contributed to this failure, but American radar played crucial roles. American destroyers detected Japanese ships at ranges exceeding visual distance, permitting coordinated torpedo attacks that disrupted Japanese formations. American aircraft, directed by radar controllers on the escort carriers, maintained continuous pressure on Japanese ships, forcing evasive maneuvers that broke unit cohesion. American gunfire, directed by radar fire control systems, achieved hits at ranges where Japanese optical systems struggled to identify targets through smoke and rain squalls. When Kurita withdrew, convinced he faced a much larger American force than actually present, American radar's psychological impact contributed to his decision. The same sensors that provided tactical advantages created an aura of American omniscience that undermined Japanese commanders' confidence. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By late 1944, the strategic situation facing Japan had become catastrophic. American submarines, equipped with sophisticated radar, had devastated Japanese merchant shipping. Over 600 Japanese cargo vessels and tankers had been sunk, severing supply lines that fed Japan's war industry. Without imports of oil, rubber, and raw materials from Southeast Asia, Japanese aircraft production declined, even as American production accelerated. Japanese pilots, lacking fuel for training, faced American aviators with hundreds of combat hours experience. Japanese warships, unable to sortie due to fuel shortages, remained in ports where American submarines and aircraft could destroy them at leisure. The electromagnetic advantage represented by radar had contributed to this strangulation, but it was one factor among many demonstrating American material superiority's crushing weight. Commander Shimada received orders in November 1944 to return to Tokyo for assignment to the Naval Technical Research Department's Electronics Division. His expertise in analyzing captured American equipment was needed to accelerate Japanese countermeasures development. The assignment carried implicit acknowledgement that his Kwajalein report had been accurate and prescient, but it also revealed how desperate Japan's situation had become. Officers with Shimada's technical knowledge were rare, and pulling him from frontline intelligence work indicated shortages of qualified personnel approaching crisis levels. Tokyo, in November 1944, bore little resemblance to the confident capital Shimada remembered from his departure 2 years earlier. American B-29 Superfortress bombers had begun systematic attacks on Japanese cities. The first major raid, on November 24th, targeted aircraft factories around Tokyo with incendiary bombs that started widespread fires. Air raid sirens sounded frequently. Blackout curtains covered windows. Food rationing had tightened to near starvation levels for civilians. The pervasive optimism of 1942, when Japanese forces conquered Southeast Asia in 6 months, had vanished, replaced by grim determination mixed with suppressed fear. People still believed in ultimate victory, the government's propaganda insisted. Japan would prevail through superior spirit, but quiet conversations revealed doubts that official channels never acknowledged. The Naval Technical Research Department occupied facilities scattered across the Tama region west of Tokyo, positioned to reduce vulnerability to American bombing. Shimada reported to Captain Takao Nakamura, who directed the Electronics Division's Radar Countermeasures section. Nakamura, a former electrical engineering professor at Tokyo Imperial University, had been mobilized into naval service in 1943 when Japanese leadership finally recognized that technological competition might determine war's outcome. His section had grown to over 80 scientists and technicians, working on projects ranging from radar detector systems that might warn Japanese ships and aircraft of American radar transmissions, to jamming equipment that might blind American sensors, to improved Japanese radar designs that might narrow the performance gap. "Your Kwajalein report reached us in March," Nakamura said during their initial meeting. It confirmed intelligence from multiple sources, indicating American radar superiority exceeds our previous estimates by wide margins. Your analysis of the SG surface search radar was particularly valuable. We had suspected centimeter wavelength radars from signal intelligence, but lacked technical details about power output and antenna configurations. Has the analysis influenced development priorities? Shimada asked. Nakamura's expression darkened. Priorities have been influenced. Resources have not. The Naval General Staff acknowledges American radar advantages, but industrial capacity to manufacture countermeasure equipment or improved radar sets remains severely constrained. We design promising systems that cannot be produced in meaningful quantities. We identify vulnerabilities in American equipment that we lack capability to exploit. We recommend tactical modifications that commanders sometimes implement, but more often ignore because they conflict with traditional doctrine. Then, the situation is hopeless, Shimada said, the words emerging before he could reconsider their implications. Strategically, perhaps, Nakamura acknowledged. Tactically, we still have opportunities to complicate American operations and impose costs that might affect their willingness to continue the war. Radar countermeasures represent one area where relatively simple devices might degrade American capabilities significantly. Electronic warfare does not require industrial capacity. Matching American scales, clever design, and targeted deployment of limited numbers of systems might achieve disproportionate effects. Nakamura led Shimada through the laboratories where electronics division teams worked on various projects. One group developed the E-27 radar detector, intended to alert Japanese aircraft when American search radar illuminated them. The device, simple in concept, detected American radar, pulses, and activated warning indicators, giving pilots seconds to take evasive action before American fighters closed for attack. But production had been delayed by shortages of vacuum tubes and precision components. Only a few hundred units would be available by war's end, insufficient to equip more than a small fraction of Japanese combat aircraft. Another team worked on active jamming systems, intended to blind American radar. The concept involved transmitting powerful radio signals at frequencies matching American radar, overwhelming receivers with noise that obscured genuine target returns. British and German forces had deployed similar systems effectively, and Japanese engineers understood the principles. But implementation faced enormous challenges. Jamming required substantial electrical power, difficult to generate aboard aircraft or small ships. Effective jamming demanded precise knowledge of American radar frequencies and pulse characteristics, intelligence that Japanese signal analysts often lacked. And jammers, when activated, became beacons guiding American direction-finding equipment directly to their sources. Japanese jammers might blind American search radar temporarily, but would guide American attacks to Japanese positions unerringly. A third project aimed to develop improved Japanese radar, incorporating lessons learned from captured American equipment. Engineers had examined the SG radar components forwarded from Kwajalein and other sources, attempting to reverse engineer critical subsystems. The American magnetron design proved particularly difficult to replicate. Japanese industry could manufacture magnetrons that produced microwave frequencies, but power output and reliability remained far below American standards. Even when Japanese sets functioned properly, they lacked the sophisticated antenna designs and display systems that made American radar operationally effective. Combat Information Center concepts, which integrated multiple sensor inputs into coherent tactical pictures, required organizational and training changes beyond electronics division's authority to implement. Shimada absorbed this dispiriting tour with growing recognition that Japanese radar development efforts, while technically competent, remained hopelessly inadequate to reverse American advantages. The problem stemmed not from incompetent personnel or flawed designs, but from systemic limitations in Japanese industrial capacity, resource availability, and institutional priorities. American radar superiority reflected decades of investment in scientific education, industrial infrastructure, and technical specialization. Japan, despite impressive scientific achievements in pure research, had never developed equivalent industrial technological ecosystems. Attempting to close the radar gap during wartime proved impossible when peacetime foundations had never been established. The psychological burden of this understanding weighed heavily on electronics division personnel. These were dedicated scientists and engineers who understood electromagnetic theory as clearly as their American counterparts. They designed systems incorporating advanced concepts, but they watched their designs languish in laboratories while American equipment flooded across the Pacific in quantities that overwhelmed Japanese defenses. The frustration of possessing knowledge without power to implement it created corrosive despair, masked by professional dedication to increasingly futile assignments. Over the following months, Shimada worked with Nakamura's team, analyzing captured American equipment as it reached Japan through various intelligence channels. Each examination confirmed American technological superiority across multiple dimensions: vacuum tubes of exceptional quality and reliability, precision-machined components manufactured to tolerances Japanese industry could not consistently achieve, antenna designs incorporating sophisticated electromagnetics principles applied through engineering excellence, display systems providing clear, usable tactical information even under combat stress, and integration every American radar set designed to interface seamlessly with other equipment, creating comprehensive sensor systems rather than isolated gadgets. The captured equipment also revealed American production philosophy fundamentally different from Japanese approaches. American designs prioritized operational effectiveness and maintainability over technical elegance. Components used standardized dimensions and connections, enabling field repairs by technicians with moderate training rather than requiring factory-level expertise. Instruction manuals provided clear, detailed maintenance procedures accessible to ordinary sailors rather than graduate engineers. American systems were designed for operation by average personnel rather than technical specialists, recognizing that modern warfare required distributing sophisticated equipment broadly rather than concentrating it in elite units. This philosophy reflected deep understanding that wars were won through systematic industrial-military integration rather than individual technical brilliance. Japanese radar development had followed opposite priorities. Japanese systems, when they worked, often incorporated advanced theoretical concepts, but they were fragile, difficult to maintain, and required highly trained specialists for operation. Japan's education system produced fewer technical graduates than American universities, and those graduates often went into research positions rather than operational support roles. Japanese industry lacked capacity to manufacture precision components at scales supporting widespread deployment, and Japanese military culture emphasized quality over quantity, assuming superior individual systems operated by elite personnel would overcome American numerical advantages. This assumption had proven catastrophically wrong. American radar sets, though perhaps theoretically less sophisticated than Japanese laboratory prototypes, worked reliably in operational conditions, could be maintained by average personnel, and existed in quantities that provided comprehensive coverage impossible through Japanese selective deployment of superior individual systems. The strategic bombing campaign that intensified through spring 1945 demonstrated radar's integration into comprehensive American military power. B-29 bombers attacked Japanese cities with increasing frequency and effectiveness. Initial high-altitude precision bombing gave way to low-altitude incendiary attacks that devastated urban areas. By summer, American bombers operated almost unopposed over Japan. Japanese air defenses, crippled by fuel shortages and decimated pilot cadres, could not prevent systematic destruction of Japanese cities. American radar played multiple roles. Navigation systems guided bombers to targets despite darkness and weather. Tail warning radars detected Japanese fighter approaches, allowing gunners to engage attackers. And coastal radar pickets detected American formations, though Japanese defenders lacked resources to mount effective responses. The electromagnetic dimension of air warfare had become as important as bombs and bullets, and Japanese deficiency in radar contributed directly to the systematic destruction of Japanese urban industrial infrastructure. By July 1945, the Electronics Division had effectively ceased meaningful development work. Resources for new projects did not exist. Production of existing designs had stopped as component supplies dried up, and factory workers were diverted to emergency food production. American bombing had destroyed much of Japan's electrical generation capacity, leaving laboratories without reliable power. Personnel faced malnutrition as food distribution collapsed. The war's outcome had become inevitable, though government propaganda still, to insisted victory remained possible through spiritual determination. Shimada spent those final weeks preparing technical documentation for whatever authorities would administer post-war Japan, ensuring that Japanese radar development history would not be lost entirely. It seemed a futile gesture, but professional obligation demanded completion of assigned tasks regardless of outcome. Japan's formal surrender on September 2, 1945, brought both relief and devastation to Electronics Division personnel. Relief that the slaughter had ended. Devastation that years of effort had produced nothing except documentation of technological inadequacy and industrial failure. American occupation forces quickly identified Japanese radar facilities as intelligence priorities. Teams from the United States Strategic Bombing Survey arrived at Tama in mid-September, beginning systematic evaluation of Japanese electronics capabilities. Shimada and Nakamura cooperated fully, providing technical briefings and demonstrating Japanese radar systems that American evaluators examined with professional interest but little concern. The assessment team's informal comments revealed their conclusions before formal reports appeared. Japanese radar technology had been comprehensively inferior throughout the war, and the gap had widened progressively as American development accelerated while Japanese capabilities stagnated. American interrogators showed particular interest in Japanese understanding of American radar capabilities. How much had Japanese intelligence known? When had they learned it? What had been Japanese responses? Shimada described his Kwajalein discoveries and subsequent analysis. The Americans listened carefully, taking detailed notes. Their questions revealed that American signals intelligence had tracked Japanese radar development continuously, aware that Japan understood American capabilities but lacked resources to counter them effectively. This created the situation where both sides knew the other's technical status, yet knowledge did not influence war's outcome because technological superiority derived from industrial economic factors immune to intelligence collection or tactical adaptation. The post-war analysis, conducted by American technical intelligence teams, confirmed what Shimada had concluded from examining captured SG radar specifications 20 months earlier. American radar capabilities had exceeded Japanese equivalents by factors of 2 to 10 across every relevant metric. American industrial production of radar equipment had exceeded Japanese production by factors of 50 or more. American integration of radar into comprehensive combat systems had proceeded smoothly, while Japanese efforts remained fragmented and incomplete, and American ability to continuously improve designs through iterative development cycles had created accelerating advantages that Japanese industry could not match. The electromagnetic dimension of warfare had decisively favored America, and this advantage had contributed substantially to Japan's defeat. In retrospect, the story of Japanese radar development reveals harsh lessons about technology's role in modern warfare. Technical knowledge alone proves insufficient without industrial capacity to produce equipment at operational scales. Individual brilliance cannot overcome systematic disadvantages in education, infrastructure, and institutional organization. And awareness of enemy capabilities provides minimal advantage when resources to exploit that awareness do not exist. Japan had scientists capable of understanding electromagnetic principles as clearly as any in the world. Japan had engineers who designed sophisticated systems incorporating advanced concepts, but Japan lacked the integrated industrial technological ecosystem necessary to transform laboratory prototypes into war-winning capabilities deployed at scales that mattered strategically. The radar gap between America and Japan was ultimately a manifestation of deeper gaps in industrial organization, technical education, and institutional priorities that decades of catch-up development could not overcome during wartime urgency. American radar superiority reflected investments begun decades before Pearl Harbor, when Japanese leadership still believed spirit and training would triumph over material factors. By the time Japanese commanders recognized technology's decisiveness, the war had progressed beyond any point where crash development programs could reverse established advantages. The examination of captured radar components at Kwajalein had revealed this truth to Commander Shimada in February 1944. The following 18 months simply documented the inexorable consequences of technological inferiority combined with industrial inadequacy and resource scarcity. The human cost of this technological asymmetry is difficult to quantify precisely, but undoubtedly substantial. Japanese ships, detected by American radar and destroyed by radar-directed gunfire, represented thousands of sailors who died in battles American sensors made unwinnable. Japanese aircraft intercepted by radar-directed fighters represented hundreds of pilots whose deaths served no strategic purpose except delaying inevitable defeat. Japanese cities, bombed by radar-navigated bombers, represented hundreds of thousands of civilians, whose deaths resulted partly from Japanese inability to defend against technologically superior attackers. The electromagnetic advantage provided by American radar had direct human consequences measured in lives lost and suffering inflicted. For Japanese officers like Commander Shimada, the war's end brought complex emotions: pride in professional service, shame at defeat, grief for comrades lost, relief that slaughter had ceased, and peculiar satisfaction that technical assessments had proven accurate, even when accuracy brought no comfort. Shimada had told his superiors in March 1944 that American radar superiority presented advantages Japanese forces could not overcome. Events had validated that assessment completely, but validation provided no solace. Being correct about inevitable defeat offered no redemption for the defeat itself. Technical accuracy could not resurrect the dead or restore what the war had destroyed. The post-war reconstruction of Japan, overseen by American occupation authorities, ironically benefited from the very industrial technological capabilities Japan had lacked during the war. American expertise, American capital, and American organizational methods helped rebuild Japanese industry along modern lines. Japanese engineers, many of whom had worked in electronics division and similar organizations during the war, applied lessons learned about American approaches to design, production, and quality control. Within a decade, Japanese electronics industry had transformed from wartime inadequacy to global competitiveness. The seeds of that transformation had been planted during those bitter months when Japanese technicians examined captured American radar and recognized the systematic superiority of American industrial technological ecosystems. Understanding defeat's sources provided foundation for eventual recovery, though at cost of accepting humiliating lessons about pre-war and wartime Japan's technological limitations. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.